Hi everyone, how are you all? It's good afternoon. So, in today's class, we are starting magnetic effect of current. Before that, I will just ask you whether am I audible or not? Is my voice clear to everyone? Is everything set? So we can start further. Okay. So, what is the chapter magnetic effect of current? This is the chapter fourth of your class 12 physics. Okay. First of all, we will discuss about what are the topics that we are going to discuss in this chapter, or we can say what is the syllabus of this chapter. So, syllabus, if I talk about, we will discuss mostly about magnetic field. If broadly, I will say, we will discuss about magnetic field and magnetic force. These are the two things that we are going to discuss. So, broad list is on your screen. In magnetic field we will discuss about what are the sources that can create magnetic field and how to calculate that particular magnetic field created by a source, and then this magnetic field, the amount of force that is being created by this magnetic field is that we need to calculate. So that's all about the chapter, that's all about the syllabus. You can see the breakdown of the syllabus here. So now moving further for the first topic. First of all, we should know what is actually electric field. So if I say till now from the class 10th basic things, you know that whenever there is a magnet, whenever there is a magnet, it creates its surroundings. And due to these surroundings, a magnetic field is created. So what is magnetic field? I will say first point about this, these surroundings near a magnet. Now, one more thing that is very interesting happens. What happens is that some scientists found that a current carrying conductor also creates something similar to the magnetic field. So, is my point clear? The new interesting thing is that a current carrying conductor also creates the same field as the magnetic field. So, second point is, I will say, surroundings near a current carrying conductor. Now, what is the specialty of current carrying conductor? It contains moving charges. So, can I conclude one more thing? Surroundings near a moving charge. Now, if I conclude the things, what is magnetic field? The surroundings either near a magnet or a current carrying conductor or a moving charge is known as magnetic field. What it does, it exerts force on similar type of things, like it can exert force on magnet, it can exert force on current carrying conductor, it can exert force on a moving charge. So from this particular discussion we can conclude one thing here, that a current carrying conductor or a moving charge creates magnetic field. What it does, it exerts force on magnet, on current carrying conductor or a moving charge. Clear? So this magnetic field is denoted by this symbol B. It is a vector quantity and its unit is Tesla. Unit is Tesla and symbol for this unit is capital T. I think till now every point is clear. So what are the conclusions from this particular first slide? That a moving charge creates magnetic field. Everybody knows that charge at rest, charge at rest creates electric field. Everybody knows from the electrostatics. Now, if it is in motion, then it creates magnetic field. That means Q in motion creates magnetic field. I think this point is clear. So now, till now, we know that a moving charge creates magnetic field. How it is represented? It is represented by symbol B. It is a vector quantity and its unit is Tesla. Now, moving further. Now, what we know that current carrying wire creates magnetic field. How much magnetic field is created by such a current carrying wire? We will show you. In this topic, we will discuss about that. For example, now try to listen each and every point very carefully. What I'm saying, let's suppose this is a current carrying conductor. It may be of any shape. So let's suppose it has a current I in it. And there is a very small element DL on this current carrying conductor. Due to this, we need to find the magnetic field at a certain point. Let's suppose this point is P. We want to calculate the magnitude of magnetic field at this point. So this distance, let's suppose, is R. Clear? And this angle is theta. So before moving further, I just want to clear few of the terminologies that is going to be used in this particular topic. First of all, the term current I and this DL, this combined term IDL, we are going to call as current element. Remember it with me. It is going to be called as current element. Very good. Now, another big thing here is this IDL is considered to be a vector quantity. That means it must have a direction. I will discuss about the direction. So this is known as current element and it is a vector quantity. So what is the direction, sir? Direction of this current element is along the tangent at DL. That means you need to draw a tangent at DL and that will be the direction of your ideal vector. Now, if I show you, this is the DL and if I draw a tangent at this point, this tangent will be something like that. So in the direction of current, along the current, this is going to be the direction of IDL because current is going downward. If current was going downward, then the arrow will be in the downward direction. Clear this point? Now, the second term that is going to be used here is R that you can see on your screen. This R. This R is the position vector of the point where we want to calculate the magnetic field. I think this point is also clear where we want to calculate the magnetic field. This is that point. Now, according to Biot-Savart law, the magnetic field at point P, the magnetic field at point P will be, let's suppose this element is very small and everybody knows DL is a very small element. So the field will also be very small. I am writing it as dB is equals to, field is a vector quantity, mu naught divided by 4 pi, vector IDL cross R divided by R cube. This is the standard form of Biot-Savart law. Just note it down, make a note of it. What is this? This is the vector form of Biot-Savart law. How much field a current element can create. How much field a current element can create. Now, there might be few doubts in your mind about the terminologies used. So I will clear one by one. This mu naught is known as permeability. Permeability of free space. This mu naught is known as permeability of free space. And the value of this complete term, that is mu naught over 4 pi, is 10 to the power minus 7 Tesla meter per ampere. So try to write it down. This is the value of mu naught over 4 pi. I think till now every point is clear. Okay. One more thing that I will say, if you can see, this is the vector product. This is what? This is the vector product, IDL cross R. We know that A cross B is AB sine theta. So we can write it as dB is equals to mu naught over 4 pi IDL R sine theta divided by R cube. So you can cancel out this R and this square term. So what it become ultimately, dB is equals to mu naught over 4 pi IDL sine theta divided by R square with a direction. Let's this direction is n cap. So now everyone should tell me whether you have studied this chapter in your class or not. You should comment, or you can raise your hand as well. Okay. Now, first of all, in your notebook, try to note down the formula because this is going to be used in the next slide or next upcoming more and more slides. This is going to be used. So this is in vector form. This is general form. Clear. Moving further. So from this slide, what we can conclude, we have learned two or three things. One is what is the direction of IDL. IDL is a vector. Its direction is along the tangent in the direction of current. Second point, we have learned that what is mu naught permeability, what is the relation of Biot-Savart law, what we can calculate using Biot-Savart law, we can calculate magnetic field due to a very small element. I think everything is clear till now on this slide. Moving further. Now, what are the punchlines that we can conclude? That's a very good thing that you should focus on. First of all, if I write the formula again of the Biot-Savart law, that is dB is equals to mu naught over 4 pi vector IDL cross R divided by R cube. This is vector. Now, first thing that you should note down as a punchline, that is field is a vector quantity and it is being calculated using the cross product IDL cross R. So the direction of field, I'm writing field as a B, will be same as the direction of vector product Which vector product IDL cross R? Now, if I repeat this length, this term, this statement in Hindi, then what it will be? The direction of magnetic field, जो डायरेक्शन मैग्नेटिक फील्ड की होगी वो क्या होगी? वो सेम होगी जो वेक्टर आईडीएल क्रॉस आर की होगी. नाउ रिकॉल द क्लास 11th when you have learned that how to calculate the direction of vector a cross b. In class 11th you have learned that how to calculate the direction of a cross b. So this is the way you are going to calculate the direction of magnetic field by calculating the direction of, let's suppose this is vector a, this is vector b. Clear? This is the first point you should remember. Now there is a second point, second punchline. This is again related to vector product. For example, you can see that if I do a vector product A cross B, if I do a vector product A cross B, and let's suppose the result comes out to be C. Result comes out to be C, let's suppose. So in this situation, what is the punchline? That the result C is perpendicular to A and C is perpendicular to B. This is the conclusion that you have made in your class 11th lectures. Now I am repeating it. The resultant of A cross B, which is C here, is perpendicular to both A and B. That means जिनका multiply, जिनका vector product किया है, उनका result उन दोनों के ही perpendicular होता है. Is the statement clear? Now we are multiplying IDL and R, and result we are getting as field. So what is the conclusion? That magnetic field is perpendicular to IDL and magnetic field is perpendicular to vector R. So I hope these 2 points are very much clear to everyone. Clear to everyone? Okay. So what are the 2 punchlines? How to get the direction, and what is the another punchline? That magnetic field is perpendicular to both current element and the position vector. Now it's your turn to answer few things. Okay. So there is a question on your screen. What it says, okay, find the direction of field, magnetic field. If I write B, that is magnetic field due to current element DL. So there are two diagrams on your screen. Take it one by one. So I am explaining one part. Like this is an element DL, and you want to calculate the direction of field. Where you have to find? At the center. Where you have to find? At the center. So let's start. First of all, we will find the direction of IDL. So current I is this way. I have to draw a tangent. So I have drawn a tangent here at the DL. What will be the arrow of this tangent? In the direction of current. So this is IDL. Next is position vector of the point. So point is the center. So join DL with the position vector R. So this is R, this is IDL. Now, how to get the direction of IDL cross R? How to get the direction of magnetic field? Just take your right hand. There might be a situation you have inversion will be there. I am taking my right hand. It might seem that I am taking my left hand. So try to follow with me. Try to follow the commands that I am giving right now. I am just behaving like a commander here. So just take your right hand and put the fingers, these fingers in the direction of IDL. Just try to put these fingers in the direction of IDL. So I am putting the nails of my fingers of which hand? Right hand in the direction of IDL. So that's it. That's it. You can put it in different ways like this. These are various ways in which you can put. Are you getting my point? Your hand can rotate at least by 180 or 300, 360 degree if you can. So I am putting my hand, my fingers, my nails in the direction of IDL. Now, second thing to note down, turn your palm, turn your palm in the direction of second vector, which is R. So R vector is downward direction. So I am turning my palm, you know that this is palm. I am turning my palm in the downward direction, keeping the nails in the same direction of IDL. So this way. Now curl your fingers. The thumb will indicate the direction of magnetic field. So thumb is coming towards me. That means coming out of the screen. So coming out of the screen, I will say that is outward to the paper. That is outward to the paper. And this outward to the paper is represented by a dot inside the circle. Will be represented by a dot inside the circle. Are you able to get? Now, it's your turn to get the direction for this second DL. Again, if I say current is flowing in this direction, this is given. Now draw a tangent. This is IDL. Second step is draw a position vector starting from DL. Join the point where you want to calculate the field. So this is R. Now put your right hand fingers or the nails of the right hand fingers in the direction of IDL. So I am putting it in the right direction according to my screen. You might see a different version of me on your screen. So I regret these things. This is the problem of the online inversion process is there. So just assuming you are following my command, put the right hand fingers, the nails of the right hand fingers in the direction of ideal. I am putting it. Now turn your palm. My hand is visible to you, I think. Turn your palm in the direction of R. So R is in the upward direction. I am turning it this side and curl your finger. So thumb is again in the outward direction. So this for this second element, B is again in the outward direction. Is it clear to everyone? Now, what is your task? I'm explaining the second question. I'm giving it to you in homework, and you need to comment on that. First of all, try to understand this loop. This is again a circular loop which has a current I. Now, some portion of it is made dotted. What does it mean? Look at me again. This loop is placed in the YZ plane. This loop is placed in the YZ plane. YZ plane means you can imagine it like a loop placed in front of you like that. Can you see the hand gestures like that? Or half of the portion like this. Half of the portion of this loop is behind your screen and half is in front of your screen. Clear? So the portion which is behind your screen is made dotted and the portion which is made solid is in front of you. That's what is the representation. I think clear. Okay. So you need to find the direction of magnetic field at this center point. Clear? Due to this current element DL. Moving further. Similar is the case for this. These two are again your homework. You need to build your concept. If you need any help, you can ask me in the next class. Right now, I am moving further. Now, we are moving further for the second concept, that is field due to a circular loop. Field due to a circular loop. Now, listen to me again. Let's suppose there is a circular loop. Okay. And somehow it has a current, let's suppose I. Clear? And the radius of the loop is R. Radius of the loop is R. Clear, sir? What you need to do, you need to find the magnetic field at its center. I am doing the derivation thing for this particular topic. After that, we will not drive the relation because you can learn those relations. You can learn to drive those relations in your classes. The important things, the important derivations I will discuss here only. So this is the first derivation that I am discussing here. Okay. Now, till now, what we know that how to calculate the magnetic field due to a current element, due to a very small element, the Biot-Savart law. We don't know how to calculate magnetic field of a circular loop. So for that, I am just taking a very small circular loop, very small element here. Of what length? DL. Yes, sir. What is the process that I am going to follow here in my mind? Just put me the thinking that I am putting here, you should follow the same thinking. What I am thinking that I will calculate the field at the center due to this small element. Okay. We will calculate the field due to this small element. After that, what we will do? We will take another element. We will take another element of this DL, this DL. So how many DLs can be formed? We can form a lot of DL here. Okay, sir, that is very clear. And then we will add these fields due to individual DL and we will get our result. So this is very lengthy process. How many DLs we can take? For that, there is a simple process known as integration. There is a simple process known as integration. So I am explaining the process of integration. So I will just redraw the diagram. Let's suppose this is the circular loop. I think process is clear to everyone. Radius is R. This is the center. And I have taken a very small element of length DL. Current given is I. Okay. So what is the direction of IDL? This is the direction of IDL. What is the direction of R? This is the direction of R. The angle between IDL and R is, you can see that this is 90. Tangent and radius always make 90-degree angle. So the magnetic field dB is equals to mu naught over 4 pi IDL sine 90 over R square. What is this distance R? This is radius now. So this is R square. Sir, what is the value of sine 90? Sine 90 has a value of 1. Clear? So dB is equals to mu naught over 4 pi IDL by R square. Now, this is magnetic field. What is the direction of this magnetic field? We have learned that you can solve it using right hand thumb rule, and this is coming out to be in the outward direction. This is in the outward direction. Now, listen to my next point. We need to add the magnetic field of each DL. Now, field is a vector quantity. You can add these quantities only when they are in the same direction. Otherwise, you need to follow the vector addition rules, the parallelogram rule, or there are other certain rules there to add. So first of all, we need to check whether the direction of each field is same or not. So let's consider another element here. You must be very sure what I am saying. Let's consider another element opposite to the first element. So if I see the IDL will be here, Again R is there, and if you check IDL cross R, the direction is again same as the first one. That means all DLs must have the same direction. All DLs will create field in the same direction. All DLs will create field in the same direction. So we can directly add that and we can integrate it. So net field is equals to integration of dB. And if you integrate it, you can put the values integration mu naught over 4 pi IDL by R square. So you can take out the constant, that is mu naught by 4 pi I by R square integration of dl. This is what net magnetic field at the center. Now integration of dl means addition of all these small elements, and if you add these small elements, it will become circumference. So B is equals to mu naught by 4 pi I by R square 2 pi R. You can cancel out the things R and R, pi and pi. So what it will become? B is equals to mu naught I divided by 2R. This is what the magnetic field at the center of a loop. Try to note down the formulas because these are very essential. Mu naught I over 2R. What is mu naught? Mu naught is the permeability of free space. Clear? Moving further. Now, the question arises, sir, this is complete circular loop. What if loop is not complete? It's just a arc. So this is another concept I will say. Let's suppose there is an arc. Let's suppose this is an arc. Okay. If this is an arc, let's suppose it makes an angle theta at the center and it carries a current I. And it carries a current I. Okay, sir. Then what will be the field at the center? Let's suppose its radius is R. O is what? Center. So for this particular case, try to remember the relation B is equals to mu naught I upon 2R. That is the field due to a complete loop multiplied by theta by 360. Theta is this angle in degrees divided by 360 and you will get your desired result. You will get your desired result. This is the field due to a circular arc. Is this thing again clear to you? Done. Now, one more thing that I will discuss here before moving further. Just listen to me very carefully. First of all, remember this relation. Now I will talk about the direction of magnetic field. The easy way you can get the direction of magnetic field for a circular loop. The easiest way to get the direction. Now, what is that easiest way? Again, don't get confused. Don't get confused. Just listen to me. Take your right hand again. Take your right hand. For example, this is a circular loop. This is a circular loop. Just for example. And it has some current I running in this direction, that is anti-clockwise direction. Current is I. Now, just take your right hand and put in the same plane of the loop. Put in the same plane of the loop. And do whatever, but listen my second step. Try to curl your fingers. Try to curl your fingers in the direction of current. In the direction of current. Okay. So In this particular diagram, the current is moving in the anti-clockwise direction. So I am curling my right hand fingers in the anti-clockwise direction. And the thumb is coming towards me, or you can say coming out of the screen. So that means direction is outward. Now, if I repeat the same question like this one, in this diagram, current is moving in the clockwise direction. So what you should do, just take your right hand and try to curl the fingers in the clockwise direction. So you cannot turn like that. For that, you need to turn your hand and you are just curling the fingers. Is my hand gestures visible to you, everyone? So you are curling your fingers and thumb is coming into the screen. That means into the screen, or you can say into the paper. Into the paper, that means it is represented by a symbol cross. So for both of these situations, are you able to understand the direction of current, direction of magnetic field? So let's do one more quick question. Let's suppose there is a circular loop. Do you know what is this loop? I have explained already. This is a loop placed in the YZ plane, and it some part of it is inside the plane, inside the paper, you can say, or some is outside. Let's suppose it has some current like this one, and you want to calculate the direction of magnetic field at the center O. So again, do one thing, try to see my gestures. The current is this is the loop now. Current is coming in this way. Current is revolving in this way. So I will curl my right hand. You can see that. I will curl my right hand fingers in the same way. I will curl my right hand fingers in the same way and thumb is going in this direction. So this is the direction of magnetic field, which is right side. This is the direction of magnetic field. This is the direction of magnetic field. Are you able to understand? Now it's time to do some questions here. These are the checkpoints, the things that you have learned. We have to solidify those things. Okay. Okay. So there is first question on your screen. What it says. Okay. Question says, find field at the center O due to the two circular arcs as shown in the diagram. There are two circular arcs. Let's suppose this is PQ and this is R and S. These are the two circular arcs. Okay, no problem with that. You must know the formula of the field of the circular arc. So what is the formula that you must know? That field due to a circular arc is given by mu naught I over 2R into theta by 360. This is the relation. Okay. Now, second thing, there are two arcs. So you will calculate field due to these two arcs separately. Let's suppose this is arc 1, this is arc 2. So you will calculate field of arc 1 and then calculate field for arc 2. Then add these two fields according to the vector addition. This is just the principle of superposition that you have studied in electrostats while solving the questions of Coulomb's law or the electric field. The same way we are going to calculate here. So first of all, I'm going to calculate the field of the first wire. Field of the first wire B1 is mu naught. What is the current in the first wire? You can say I. What is the radius? Radius, you can say radius is A. Angle is 60 divided by 360. So that will be 6. That means mu naught I by 12A. Clear? Now, tell me the direction of magnetic field. The current is revolving in this direction. So I will curl my right hand fingers. I'm again saying just follow my commands. Don't follow the visuals actually, because it might seem different to you. Current is flowing anti-clockwise. So I am curling my fingers in the anti-clockwise direction and thumb is outward. So the magnetic field is in the outward direction. Very good. Now we will calculate the magnetic field due to the second loop, that is B2. Again, relation is mu naught. Current is 4I divided by radius is this time 2A. 2 is already there and radius is 2A into theta is 60 by 360. So if you can solve it, this is 6. This 2 and 2, 4 and 4 will be cancelled. So that is mu naught I by 6A. And direction of this field will be inward. So the net field, I will say net field will be, the outward vector is positive z-axis, the inward vector is negative z-axis. So I will say that is B1 minus B2, and you can solve it mu naught I by 12A minus mu naught I by 6A. Can you solve it? I can see that it will be mu naught I by 12A of negative sign. What is the meaning of negative sign? What is the meaning of this negative sign? This negative sign indicates that net field is into the plane. So I will write as into the plane or make a cross symbol. Is the first question clear to you? This is the very basic question. The similar kind of question with little bit of tweaks was asked, or these type of questions were asked a lot of times in your mains exam. So try to clear things out and watch this video again and again, moving further for the next question. Before coming to that question, I will ask another question. Okay, this is a difficult one. Okay, so let's do it because we have to finish it off. Okay, I think this question, I'm telling you the answer. Try to solve it out in your homework because this is a standard question. Solve in homework, but I will tell you the concept here. What will happen? What is going to happen? Because it is time-taking process to solve this particular question. What's happening here? This is a circular loop. Okay, conducting circular loop basically. Now there is a cell. Let's suppose its potential is V or EMF is V. This is connected at these 2 points. Let's suppose P and Q. That means a cell is connected across any 2 points of the loop. I am saying the word any 2 points of the loop. You have connected a battery. Now the question says, find the magnetic field at the center. For magnetic field, there must be a current. So this battery will supply some current. Let's suppose I. When it reaches point P, current is divided in 2 parts. Let's suppose this, in this part current is going I1 and in this part current going is I2. Clear? There is a division of current. The next thing that I will tell you, these are the 2 parts of the wire, part 1 and part 2. Let's suppose The resistance of part 1 is R1 and resistance of part 2 is R2. Length of part 1 is L1 and length of part 2 is L2. Clear? Is this clear? So the standard result says the magnetic field at center will be zero. Try to remember the standard result. This is a standard result. Whenever you connect a battery across any 2 points of a circular loop, the net magnetic field is zero. Either you can connect, let's suppose this is the circular loop and this is the diameter. You can connect the battery across these diametric points or diametrically opposite points. Field will be zero again at the center. You can connect the cell at these 2 points. Field will be zero. Every time field will be zero. So your task is to complete this question that how field is going to be zero. From my side, you should remember this result. Clear? Now, moving on to the question which will enhance your thinking skills. This is a very good question asked in the JEE exam, that was previously asked in the JEE exam. This is PYQ basically. So what it says, just read out the question very quickly. There is a disk of radius r, has a uniform charge of charge density sigma. That means it has some charge of charge density sigma. It is rotated. Now, first of all, draw the disk. I'm going to draw the disk. This is the disk. This is the disk. Now, it is rotated with angular velocity. This is not W, this is omega actually. Rotated with some angular velocity, omega. About an axis passing through its center and perpendicular to the plane. That means axis is somewhere here, perpendicular into the plane. Sorry. Find field at the center of the disk. Now this field, this ring, if I say, has some charge which is uniformly distributed like this. If I can draw these charges like this. Like this. And this disk is rotated with some angular velocity omega. And you have to calculate the magnetic field. So what we should do, first of all, we should know how magnetic field is created. Magnetic field is created whenever there is a current. So can you see the current here? There is only charge. Can you see the current here? First question is ask yourself whether it can create magnetic field or not. The answer lies when this disk rotates. Can you see is rotating? Current will create. First question very small
assignment. रुको, I'll do it. मैंने उसमें तो ऑफ कर दिया है इसमें. We'll just keep note of all these things so that we can inform the teachers.